this is not like a polished lecture because this is still a work in progress. This is some of the spectra that we're analyzing for a paper that I'm writing with Geraldine Monjardet in Forensic Science. And so I haven't got all of these spectra fully assigned, all the peaks, because it's 150, 160 vibrational modes, and they're all overlapped. And there's no way you're going to get every one of those assigned. Now we can calculate them in Gaussian, so we can have a Gaussian understanding of where they are, and you can look at all of them. They're all so close together that they're just all under one peak. So it doesn't really do you much good to say, you know, to video, like produce a video on every one of those vibrational modes because there's so many and they're so similar. So I wanted to bring this to you guys just to kind of talk about how it gets complicated with bigger molecules. So that's number one point. And two, to clarify the in phase, out of phase thing. Okay, so now we have a big enough molecule that we can have in phase and out of phase, and it'll actually mean something. Okay, so, and then third, I want to introduce you to this guide I put up in the lecture materials. You might have saw the book by Socrates, The Characteristic Group Frequencies. And so I want you guys to be able to refer to that in your research if you do IR or Raman on any of the organic molecules. There's a chapter associated with CH stretches, a chapter associated with ether groups, a chapter associated with carbonyls, a chapter for aromatic compounds, and so on. So you can work your way through all the different functionalities of your molecule, and you can go to those various chapters and you can see where those peaks would be located. Okay. And so we're going to be looking at, this is our goals for the paper: identify the molecular motions that produce the main features in the spectrum, and emphasize those motions and features that allow discrimination between cannabinoids. For example, that idea of, does this publicly available CBD gummy contain a prohibited amount of THC? Could we do that with spectroscopy? Still unknown. I don't know. Okay, so here's the different structures that we have, that we have standards of. Okay, there are other cannabinoids that probably, my friend Barbara Koenigsberg, she consults with me in cleaning research and so on. And we had a webinar with Alkanox, and Alkanox sells detergents. And they internally, they thought, well, do we want to get into this market or not? And so they made a corporate decision to get into this market to clean the extraction equipment to sell to the people that are doing the extraction equipment for all of these oils. I mean, this is an oily, viscous substance that comes out of these plants, and do the separations and so on. And that glassware has to be cleaned, and Alkanox is a great detergent for cleaning glassware. And so they held a webinar, and Barbara's comment and Michael, who from Alkanox, can concur. She says plants produce complicated molecules because, in her phrase, plants don't poop. Okay. So think about all the things plants build. The only thing that they get rid of in terms of waste is oxygen. Everything else stays in the plant. And that's kind of interesting. So that's why plant chemistry is so incredibly complicated. And if they can find a mechanism that through just natural selection that enhances that plant's survivability, then these other uses for these compounds can play a role in that plant's physiology. But that's why plants produce things like this that are absolutely so complicated. Is that that's according to Barbara, plants don't poop. And so they're producing all kinds of molecules with all kinds of chemistry just as they function. And so here's some relevant things that we might see in the molecules that are different between the different cannabinoids. So, you've got aromatic rings. So you've got some phenol groups. So we can see those here. It seems like all of them have at least one. Okay, so we're going to have OH peaks, OH stretches. We're going to have aromatic carbon oxygen stretches, and so on. Some have two of them. right? So this might be a distinguishing feature. Not all of them have this ether linkage. So here's an ether linkage here. So if you were to make a Venn diagram, the ether circle would contain those four molecules. The acid circle on a Venn diagram, we have THC acid and we have CBD acid. So those things have been acidified. A lot of these are the product of metabolism in the plant or outside the plant. Maybe in the body. So you have a compound, your body's trying to metabolize it, make it more water soluble so you can pee it out. One of the metabolism routes, which I'm not a toxicologist, but one of them is a common one, is to put an acid group on that molecule. And so the result will be acidification. We have a lot of differences in these olefinic groups. So that's what OLE-H is, 3 OLE-H's. Okay. So these would be these right here. And this one here. So just looking at the molecules, we can see, different features that might be relevant and might give a difference in the peaks in the spectrum. But just looking at them, we might not know, if it's, if it's going to be a high enough intensity for us to discriminate. Okay. And notice all of them have this same little tail. So this little propyl group that sticks out, those are the same for all of them. So we should see very similar CH stretching regions. We've got CH2s and a methyl group on the end. So we should see very similar signals from those. And so let's jump into the spectra. So what I've done is I've taken that group frequency table, the characteristic group frequencies by Socrates, and gone through the CH stretch region, and it says for the CH2 acyclic asymmetric stretch, this is the range. So I went in and I put this little series in Excel. I just plotted whatever the range is here and connected those two lines. And so this is a separate series. I'm just telling you how I plotted this. And then I did the negative error bars. So I said that the negative error is 100%. And so the error bar goes all the way to the baseline. And so that produces this little box that should contain a peak that is the CH2 asymmetric stretch. So this is the asymmetric stretch for the CH2s. Should appear in this region. And what do you know? Our peaks, we have very good peaks right there. That's the maximum peak in the CH stretch region because we have these CH2s right here. That's the CH2 stretch. We also have a couple over here. Okay. And then here's the CH2 symmetric stretch over here. So this is that blue region. Notice these regions overlap a little bit, so we might see some movement of this peak from one compound to another, but they all have the same little pentane tail. So that's, it's going to be the same for all of them right here. The only difference might be if it has this fused ring and those CH2s are not. So there might be a little difference in this region, but this is the CH2 symmetric stretch right here. So we can immediately identify these peaks in this complicated molecule. Then we have the CH3 asymmetric stretch, and we have the CH3 symmetric stretch. So we're very familiar with these, right? We have the asymmetric stretches and the symmetric stretches. All in this area. Yes. This is the characteristic group frequencies. So these are sort of the experimental ranges for this CH2 asymmetric stretch. Now, if you're in a molecule that's maybe pulling electron density away from that carbon or putting a lot of, a unique situation, right? Then maybe that peak would move around. And like in our calculations in Gaussian, they were hopping all over the place. The CH2s and CH3s were moving around. and we'll see that in our notes. Okay, but yes, these are this guide would be for the average set of organic molecules. Now, if you have some very strange um, functional groups that are changing the electron density on that carbon where those two hydrogens are attached, then you might see a significant shift. But we don't have anything like that. We don't have any sulfurs. We don't have any fluorines. We don't have any triple bonds or anything like that that's adjacent to these CH2s that might change their frequency a large amount. So the thing that would change those frequencies is the electron cloud on that carbon. And is something pushing electrons toward that carbon or pulling them away, that would shift the frequency. Because what about the frequency changes when I have that electron cloud on the carbon change? What is making the frequency change? This is something every one of us should be able to answer. What'd you say? Well, we're talking about a specific. Okay, so we have, what's the frequency? How do I calculate the vibrational frequency? 1 over 2 pi c square root k over mu. Okay, so this is all that goes into the vibrational frequency. So when I'm changing the electron density on the carbon, which these hydrogens are attached, which one of these am I changing? You have two options. You flip a coin. Ding! It's either K or mu. So if I had a triple bond or a double bond, I say a double bond, it wouldn't be a CH2, but you get my point, or a triple bond. What would it do to the vibrational frequency of a hydrogen on that carbon? Would that change the reduced mass of this hydrogen that's vibrating? No, because the reduced mass is the nucleus. So what is it changing? Force constant. It's the only reason that hydrogen is stuck to that carbon in the first place is the electron cloud. And if I change the electron cloud through K, I'm changing the vibrational frequency. So that's fundamental. Yeah. So this equation you should really have in your head, because it explains why the frequency moves where it moves. Yeah. It's in the region, so the double bond is changing the electron cloud around that CH bond. Yeah. Yeah, you're right. It's not a double bond to the hydrogen, but it is changing it some, and we might see a shift to the CH2 stretch and the CH3 stretches and so on. Okay. Um, Now look at some of the others. We have what is this thing? CH3, CR3 asymmetric. So what is that kind of business? Well, this is the only H I see, so it must be a methyl bonded to something that carbon doesn't have any other hydrogens on it. So that's the methyl, this methyl right here. This is a CH3, and this is a CR3. You see that? So there's 3 R groups on that carbon, an oxygen, a fused ring, and a methyl group. So this carbon doesn't have any hydrogens on it. And it's bonded to this carbon with 3 hydrogens. So this methyl here, that's a particular, so in that group characteristic, frequency, uh, characteristic group frequencies book, you have all of these little scenarios of types of CH stretches. And one of them was this, that it's a methyl group bonded to a carbon that's got other things other than hydrogen on it, all 3 of its other valences. Okay. You also have the aromatic hydrogen stretch. So we have this aromatic hydrogen. So we've got a couple of those right here. Okay. And we got 2 little peaks there too. So it might be the symmetric and asymmetric stretch for those things. We could have the 2 stretching together symmetrically or asymmetrically. Okay. This one is interesting. This R3CH. R3CH. So we have a C, R, 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 and an H. Where are those? Those are the red, these are the boxed red ones here that I have. See, we have this carbon bonded to 3 other things, and the hydrogens are omitted because organic chemists are lazy. Okay, so there's a hydrogen on there. We don't see any double bonds, and I only see 3 bonds, and so the 4th bond is to a hydrogen. And so that's an R3CH, and again, it's going to have a different force constant than a CH2 or a CH3. And so that shows up here, and we see that tiny little peak. Now that's a good one because we only have 4 out of our 7 compounds, and THC and CBD, that have those, and the other 3 don't. Okay. So is anybody? Oh, and this one down here is the OH. This aromatic OH stretch has a huge range. Look at this range. So that's pretty hard to identify. Where is the aromatic OH stretch? The OH stretch, where the O is connected to an aromatic ring. It's the phenol stretch. It can be all over the place, depending upon what else is on that ring, whether it's an ortho substitution, meta, para, multiple things. Here we have all kinds of things attached to our ring. Okay. And so it's possible that it's this one right here. Okay. Make sense? Yes. It can, that in all of the data that this book used to come up with its tables, it found OH stretches it somewhere along that whole range. So like, yeah, it could be down here, this peak, it could be down here, or it could be way up here. And so some compounds it's way up here, other compounds it's way down there. For our compound, this might be it. Okay. So so it's interesting. It's not good for um, coming at this with a blank slate like this and saying, okay, I see a peak there. What is it? I'm not going to see that peak and say, absolutely, that's an aromatic OH stretch, because there's a wide range for those. But if I see this peak right here, I say that's probably the CH2 asymmetric stretch because its range is really narrow. So that one is a good one. The narrower the range, the more consistent that vibration is in all the different compounds. So the OH stretch is not consistent for phenols. Depends upon what's on that ring, substituted on that ring. Okay. Yes.
How is this diagram different from an IR spectrum? Same
How is it?
IR spectrum?
This is infrared spectra, and this is 2 different types. So this is attenuated total reflectance. So you just put the powder on the ATR, squeeze it down. And this was the minus log R. They had it cut off at 3200. I don't know why experimentally they did, but so the dashed one is minus log R, and the dark one is ATR. The minus log R is from a microscope where they precipitated out the crystals, and then they took a spectrum of the crystals, okay, with the FTIR. Okay. And so here's the Gaussian calculation, and here's again for THC. You see, it's the symmetric methyl stretch, okay, but we have 2 of them. And so this is what I mean by in phase. We have 2 methyl groups. It's symmetric. There's nothing asymmetric about that stretch, but because there's 2 of them, they can be in phase. So that's what in phase is for. And then this is out of phase. You see, 2 methyl groups, one stretching while the other one's compressing. So that's the out of phase. So I know that y'all's molecules weren't big enough to have in phase and out of phase, but when I was writing up the plans, I was saying, talk about your spectra with terms like symmetric, asymmetric, in phase, out of phase. I was just listing the terms that we use to describe these motions. And I shouldn't have said in phase and out of phase, because y'all didn't have the possibility of having in phase and out of phase, really. You had symmetric or asymmetric, and that was it. Yeah. You could have coupled, right? You could have the bend of a methyl group coupled with the NH stretch or NO stretch, but you couldn't have in phase or out of phase. So here they are together, so you can just really lock in your brain what's meant by that. Okay. And those are the vibrational modes from Gaussian, number 150 or number 153. Any questions on that? Does that clarify things? Because we had a lot of confusion about that in our talks. I would say yes. Yeah, I would say yes. Like a CH2s, you can have them in phase or out of phase. Yeah. If they're not the same groups, then we would just say those modes are coupled. Yeah. And then you might have to define like specifically what you mean. If you wanted to say coupled in phase and coupled out of phase, you might have to say, if it's a stretching mode, it's pretty obvious that, say the NH2 is stretching while the CH3 is stretching. And if they're both stretching at the same time, I'll say, because they're both stretching, I would call that in phase. And you would just write that out in the text if you're describing it. So then looking at these vibrational modes, I went and assigned, all of these things to the CH3 symmetric stretch, the aromatic hydrogen stretches, the CH2 symmetric stretch. This was that R3. No, this was the Ollie H in our little description was over here. This tall one, and then we had the CH3 asymmetric stretches here, and then we had some others. You didn't finish the? Yeah, I did. Here's that R3CH, and then here was the aromatic. So in Gaussian, our aromatic OH showed up over here. So that was good. It was that peak that I said, could this be? Gaussian predicted that it is there. Now notice the problem with Gaussian though. All of these peaks are way below 3,000. They should be much closer to 3,000. Okay, they're way down here. They have a very similar pattern, but look at the experimental. The peaks are, they start at 3,000. They start coming up here. And Gaussian, they talk about, well, you scale the frequencies based upon the neglect of electron correlation. Well, almost all of those scaling factors are less than 1, so it just makes them even lower in frequency. So this, and again, I don't have the method here. I have to show you the model chemistry. But that was our experimental. This is our Gaussian calculation. And we did see that swap of the CH2s and the CH3s. So that's why these arrows cross. So the group characteristic frequencies for the CH3s were at low frequency and the CH2s were at higher frequency in experiment, but in calculation they were swapped. So I don't like that, but that's what it is. This is that olefinic hydrogen. Don't exactly know where that is in our spectrum. The aromatic hydrogens in our experimental spectrum, they show up between like 3010 to like 3080. That's that range for the aromatic hydrogen stretch. For Gaussian, it's calculating them way too low. It should push them up here a little bit. But that is nice. We know we have them. But it is nice that this from our characteristic group frequencies, these peaks right here are probably the aromatic hydrogens. And in the Gaussian helped us assign this one, so that's really good. And the Gaussian helped us assign this one too. So these are some very good assignments: the aromatic oxygen hydrogen stretch and the R3CH stretch. So this is if we just take a spectrum unambiguously, if we look at this region right here, we know we have one of these 4 compounds. So that's good for discrimination. At least we can knock 3 of them out of our mixture. If we wanted to determine if we had an acid or not, so we have 2 of the compounds that are acids, and this aromatic acid carbonyl stretch right here is indicative that we have CBDA or THCA. These are, again, I didn't do the vertical error bars because it just started getting too busy. And so I just deleted those off. But here's from that group characteristic group frequencies book, we have the CH WAGs. So these right here, this is a WAG. A WAG or rock or bend, I would say, bending modes. CH bends, how about that? As opposed to CH stretches. Yeah, here's the specific scissor mode right here. This blue one is the CH2 scissor. Here's the methyl deformations, asymmetric. So we have two different options going, say, in the X direction or in the Y direction. The deformations with those bending modes, the angle bends. Here's the CH WAG, R3CH WAG. The phenol WAG, so the wagging of that hydrogen. Again, a wide range on that one, so not very diagnostic. We have the acid CO stretch, so both of those have that. So that's the stretch of this bond right here. And then this one also, the acid CO stretch. And so what I'm looking for, they both, if they both have this carbonyl, then this compound is an acid, but which acid is it? Is it CBDA or THCA? I can't really use this peak because it's the same height. It's just shifted a little bit. If I had a spectra of both in my compound, I could identify, well, this peak is associated with one, not with the other. But if I just get one of these spectra, I'm not going to remember the exact shift of one versus the other. So a peak shift is difficult to use for discrimination. So I'm looking for a peak that's present in one and completely absent in the other. And that's what I have in the blue box. So THCA has this little doublet here at 1120, and CBDA does not have that at all. So that's a good way to tell between the two. So that's why I labeled it blue and call that the differentiation. So this identification of both acids with the carbonyl stretch, and then the differentiation at 1120 for CBD versus THC. And I would say a medium intensity. It's not really a strong peak. The carbonyl stretch is the strongest peak in the spectrum. So, any questions about the fingerprint region? And so here's the other three compounds, all on the same spectrum. And notice that peak here is missing. The R3 CH peak is completely missing. So I know if I don't see that shoulder in the CH stretch region, I don't have THC, I don't have CBD, THCA, CBDA. So that'd be very helpful. I don't know the psychoactive properties of these three, but if the law is focused on THC and I recrystallize whatever these things are and I look at it in the infrared and I don't see that shoulder, it's not THC. So it's not illegal, at least until laws are written for CBN or something like that. Okay, here's the fingerprint region for those molecules. Now they don't have the acids carbonyl stretch, but they still have carbon-carbon double bonds. And so we have some of these carbon-carbon double bond stretches that are showing up in this region. So this one, I just put a big question mark here. I haven't analyzed these three in this region too much. I have analyzed them enough to kind of pick spectral features that will split them apart. But like if you look at this black one, the CBC, it's got a ratio here that seems to be unique. Like this is about half of that one, whereas the other two, those peaks are either the other is taller, or they're about the same. And so I might be able to take I might be able to look at that region and split out CBC from the other two if I ask a question about it. So what I did was I went through and I created this identification tree. And so I've got spectra for you guys. And I'm just giving these to you randomly. So you have spectra of 3 of these compounds. And you get to pick out, like use the tree up there and figure out which one it is. I might have to make the screen bigger. What are you worried about? Oh, very good. Oh, goodness. Yeah. Here, press one of yours down. Okay, let's go to the first one for our question. So the very first question, the CH stretch shoulder at 2830. So look in the CH stretch region. Do you see a shoulder at 2830? So you can answer yes or no, like you can circle 2830. If there's a shoulder there, then you have one of the 4 compounds. You say yes to that, you've got THC, THCA, CBD, or CBDA. Okay. Okay. Let's do the question number 2. Look at the region of 1625 and 1585. So this is that carbonyl stretch region. If 1625 is less than 1585, that's the question. Less than or equal to. 1625 is less than or equal to 1585. If you can say yes to that, it's not one of the acid groups. It's THC or CBD. And then THC has a doublet CH stretch at 2865. And if you're too much of an angle, you can here if you want. Yes. Mhm. Which question was that? Yes. Yes. No, let's go. Y'all have good eyes if you can read that in the back.
It is, it's, oh, okay.
Yeah. Those keys.
This right here.
I can look at that though and see. Yeah. Yes.
It's drastic as instrument, so
Right.
whether.
Yeah. I think it is. I got, sorry, that could happen as well. You could look at it for a reason. It's not just a group of people. I think it's very frequency. Mhm. So, the shoulder at 2830, so it's very specific. So these are 10 and 30, so it's not. To be really good. Yes.
I think I missed something. Okay, the 2030, right here.
That's it.
Right, okay, but then
Yes.
where is this I coming from? Because all my intensities are on the decimal point. I'm not sure what this means.
Oh, okay, so it's the intensity greater than the intensity, 1585. So here's 1585, and here's the 16, whatever, 20. Something is the six, I'm asking you if it's less than, is the intensity of this peak less than the intensity of that peak?
But I'm looking at this one.
No, this is the same. This is the CH stretch, and this is the fingerprint region. No, that's it. Yeah, because this is, we're looking at this shoulder here. 28, no, 28, 30. So that's the difficulty of these flow charts because, yeah.
Yeah.
So 28, 30, so you can 30.
Yeah.
Yeah, you got a shoulder there.
I believe that, I expect it.
I just thought
So this is definitely 1 to 4.
Yeah.
And it's definitely, okay. And then it doesn't have that peak. That's the 11, whatever, 11, 20. So the no, that would be CBD. And then here, so it is one of the compounds, it's not an acid. It's a then 2865. Yeah, so the yes is peach. Okay. Okay, yeah, that was tricky. You got the, where, the 16, 14, 18. And it's less than. Yeah, okay, good. Good, good, good. So we just make sure. Second, so 16 degree. Oh, that's you. Okay, this is a different version of the. Yeah, I had to write the scheme, that would be valid from both branches. Yeah, you got it. Well, so that. Okay, that's the, yeah. Excellent. Yes. Correct, no shoulders. Mhm. Yeah, so there's no shoulders and it's not THC, it's CBD. And so then you go to the next one, so it's no shoulders, we go down, 60, 30, 14. That's right. Yeah. Yeah, so you say yes, so to the CBD. Here's CBG, And this is the correct one. You got it. Yeah. 17. Page color at 2960. But this guy right here. Very, yeah, but it's a very unique thing. Yeah. That one shows us, see if the one. So. I was really sure that. Yeah, so that's something you see that, so, you see on the. Oh. Yes. So here it's a beautiful photo. It's like your photo. So that's unique to see. We should look at the molecule and see what is it about CBDA being absorbed. You got that?
CBDA molecule.
Yes, it's definitely. It's not. Right here.
And like, oh, these citrus, yeah.
2065. Yeah, so this is a, these are very. Well, these are the same. Everybody did their question. Yeah.
I haven't actually done that. You see anything?
Oh, it doesn't have this shoulder either. It's a people. In 2830. 2830, the shoulder. Because you get the no. Yeah. Look at this. It looked like.
That is. These. Over the potters. Yeah, that's what I. These spikes over that. Yes, it's double expression. It's fine. So let's see. 16 $20. That's probably less than great. Solve that thing. Yeah. Actually, me on that is good.
Y'all can, example if you're. Okay, yeah, okay, that. That's great. Quick one. We need something in history. Just say, we have like. We learned that, yes, like, clear.
In the long run.
This is the movie is this stuff, this is show right here. See how many reasons here, there's no. So this time we have, look at the point here, you have baseball, nothing, you can get baseball, that's so. Indicated for the. So that's how the pH correct, so. 2980. 2980, so this is 2980, right there. So it's straight down, it's this question right here. Sorry. Yeah, you have to keep that. Yeah.